for example, polythene, bakelite, PVC, etc. But this time we are moving towards a new topic, that is an organic polymer, which is silicons. Okay, these are a different class of polymer as compared to, or as we compare with the previous one, that was organic polymers, simple polymers we call them. So these are different, better one to understand. We will move forward. So my topic session will be on will be highlighted towards introduction of silicons, structure of silicon polymer, what are the different structure, preparation, how we are going to prepare silicon polymers, how it is prepared, and properties of silicons, what are different polymers properties and why they are better as compared to organic polymers. And finally, we are going to discuss about use of silicon polymers, what are the different uses of silicon polymer, in what practically in what systems we are using it. So basically, inorganic polymers, these are containing organic and organic components, and these are hybrid polymers. Most such polymers are called hybrid polymers, and best example is polydimethylsiloxane. I repeat, one of the example is polydimethylsiloxane, which is commonly known as a silicon rubber. Silicon rubber is chemically, or it is known as polydimethylsiloxane. We will look in a few further slides what does it mean. Now, these are the different types of different types and uses of silicons. It is used in the form of gels, films, fibers, sponges, and it acts as photonics and nanotechnology, electronics, optical fiber, as adhesives in bones, ligaments, and microfluids, etc. These are the functions. It is widely used in different types of activities. Silicon polymers, these are synthetic polymers, which is having a big bond of a repeating silicon to oxygen bond, SiO bond, which is sometimes linked with organic site, organic group, such as methyl, phenyl, or vinyl. The basic repeating unit is known as siloxane, and the most common, which I have already discussed or explained to you, that most common available silicon is polydimethylsiloxane, which is commonly known as silicon rubber. So every silicon polymer which is to be studied are having a basic unit, basic backbone, which contains bonding of silicon and oxygen as a repeated unit. As we have already studied and we are knowing about polymers, that polymers are the repeated units of monomers. We are having a type of a monomer, and when the monomer are repeated, they lead to the formation of polymer. So here we are having a monomer as silicon oxygen bond, SiO bond. We will look further how it look like. Now, basically, what is the structure of silicon polymer? This is a basic structure what I would like to explain about. This, we are having a silicon, and it is attached with oxygen, silicon, attached to oxygen, and silicon, oxygen. So we are having a repeated unit of silicon oxygen bond, and the common chemical formula what we are having is, it is RxSiO2 minus X by 2n, where X, if X is 0, it could be it is inorganic polymer. X if 4, it goes to organometallic polymer. X 0 to 4, it goes to polymeric silicons. So it could depend upon different types of constitution and different types of side chains. Further, these are some structures I would like to explain to you. This one is rhodomic. This is rhodonite mineral. rhodonite mineral. In this, what we are having a repeated unit of SiO bond. This is the S, a big bond, and in this we are having manganese as a side chain. We are having side chains, and it goes to formation of a mineral which is commonly known as rhodonite. Whereas we have studied above bentonite mineral, in which we are having repeated or backbone unit of SiO, silicon oxygen big bond, and it is attached with barium and Ti. So this is known as commonly bentonite mineral. These organosilicon polymers, these contain chains or network of alternating silicons and oxygen and the structure, and due to some addition of some specific elements or metals, the structure or the property of the silicon changes and its use could be changed. For example, we are having another simple silicon. This one in this structure I am going to show you that this is the basic backbone structure where silicon is attached with oxygen and a repeated unit is formed, whereas as a side chain we are having alkyl group on the both sides. This alkyl group could be synthesized or could be replaced by any other group, and this is basically called silicon. Now what I would like to explain to you, this is dimethyl silicon. Dimethyl silicon means when both the alkyl group are of methyl group, so such type of silicon are known as dimethyl silicon. If anything else, any another alkyl group attached, it could be named as such as accordingly. Now, polymeric molecule in a silicon held together by very weak van der Waals force. So they are having a they are liquid nature of different viscosity, and due to this viscosity, different viscosity, it could be the form of gums or liquids or gel, etc. So in this one structure I would like to explain that this one silicon is a big bond structure. Okay, we are having big bond structure and two hydroxide group. These are two hydroxide group. So we can continue this chain with addition of another monomer unit of silane, and this is the basic big bond structure with silicon oxygen bonding, and where we are having alkyl group over here, which could be replaced by any type of alkyl group, and it will alter the property of that particular silicon and nomenclature specifically. Now further, there are different types of organosilicon polymer. It could be oil, or it could be rubber or grease, or any kind number of organic groups. So different types of group, different types of polymer we can get, or it could enhance or decrease the property, and it could be also changed with its use. Now how we are going to prepare silicons? This is a 3-step procedure. First we are having tetrachlorosilane, SiCl4. These tetrachlorosilanes are reacted with alkyl group and they form alkyl chlorosilanes. Here I am showing dichloroalkyl silane. So tetrachlorosilanes are first converted into alkyl chlorosilanes by different procedures. Okay, then this alkyl, here I am explaining about dialkyl chlorosilane. This dialkyl chlorosilane is hydrolyzed by using H2O, and both the chlorine molecules, these chlorine atoms, are reacting with proton of water molecule and moving out in the form of HCl, and the hydroxide are attached with the dialkyl silane and forming hydroxysilanes. So these are hydroxysilanes. So we have obtained hydroxysilane, and these hydroxysilanes are reacting. These hydroxysilanes are reacting together. What I would like to show you here. Hydroxysilanes react together to release out H2O molecule, and in this way we are obtaining a higher molecule. These here monomers are reacting and we are getting a polymer. This is a dimer. Now in this new compound we are having two active sites, this one with hydroxide group and another here with hydroxide group. Okay. So up till well we are having a hydroxide group in the molecule. Till then we can increase the length of this particular chain. For example, in this particular chain we are having only two monomers or two silicon. We can increase up to when we are having active group available on each side here. Now we have increased it to a higher range by slowly and careful control conditions, and sometimes it could also lead to formation of cyclic components. For example, here I am showing tris cyclodimethylsiloxane and here tetra cyclodimethylsiloxane. So in control condition we can form cyclic structure of silicon with the nature of 3, 4, 5, 6 silicon atom. Further, now in this one structure, both the monomers we are having trimethyl hydroxysilane. In this we are having three alkyl groups, and both the alkyl groups are both the molecule, the hydroxide molecule are getting reacted to form a silicon. It's dimer and it is not having any active site, so the reaction will not be proceeded, and hence this particular reaction, this reagent will not further produce any further silicon. Sorry. Now there are different properties of silicon. It is having thermal stability, chemical stability, chemical reactivity, and other properties. We'll go to it. The silicon oxygen silicon bond in silanes, it is very much shorter, and as calculated from their radii, it is very much shorter. So this indicates there is some ionic character in silicon oxygen bond, due to which it becomes very much stable. So it could have been longer, but it is shorter, and due to some ionic character, it is very much stable. This is the reason why we are using silicons in different high temperature industries or high temperature equipments, as it can withstand the temperature up to 350 degrees Celsius to 400 degrees Celsius. It does not decompose up to such a very high temperature. Now this chemical stability, higher polar character of Si bond and the ability of silicon to expand its valency shell by utilizing its g orbital, it renders polysiloxane to be acceptable by attack by several reagents. So it is not attacked by different reagents, and strong bases acids, this can depolymerize to the silicon. For example, some electron deficient salts may cause the cleavage of SiO bond as well as silicon carbon bond. So strong acid and strong base, these causes to the stability of silicons and damages the compound. When dry chlorine is attacked or is inserted to the silicons, this results into the formation of compounds with having chlorines, or we can see that chlorination of alkyl groups takes place. Alkyl groups are releasing hydrogen, and on the place of hydrogen or proton, the chlorines are get attached. Other than these above reactions, the polysiloxanes are chemically inert. These are basically inert at room temperature to the dilute acids and bases, metals and salts. So much they are chemically stable and not reactive to most of the chemicals at room temperature. But but strong acid and strong base, it causes to the chemical stability of the silicons. Further, silicons can bond. Silicon bond, this can be damaged or deteriorated by the use of Grignard's agent, as lithium. Okay, for example, we are having a particular silicon over here, okay, and this is attacked by IMGX. It is a Grignard's agent, so it damages the silicon bond and forms a MgX complex here over here. It could further be hydrolyzed to form lithium aluminum hydride. It can react with lithium aluminum hydride. So Grignard agents disturbs the or breaks the bond of silicons. Next, there are different other properties. Siloxanes are water repellent. They repel the water. That's why the glasses are coated with polysiloxanes. So the oxyatom of polysiloxane adhere to the glass, and the alkyl groups on silicon direct outwards, and it does not allow water to be absorbed on the surface of the glass. These are also electrical insulators. These are transparent and to visible light, but it sometimes absorbs ultraviolet radiations, specifically of very short range UV radiations. There are different types of uses of silicon polymers. For example, we can say silicon rubber. We are using silicon rubber for the insulators, as you have already discussed that they are electrically neutral. Silicon oil, these are used as a lubricant and different purpose. Silicon grease, it is also used as a lubrication. Lubrication for making waterproof clothes, and a pepper for making paint and enamel. This is one of the important use nowadays for which silicons are used. So this is the end of my lecture. Thank you.